Symmetry has always intrigued humans. What if I told you that there is a fascinating and mysterious eightfold pattern, a periodicity, to the symmetries of some of the most symmetrical objects in existence? I'd like to tell you about Bott periodicity. Bott periodicity is a discovery named after a Hungarian-American mathematician, Raoul Bott. It was such an exciting discovery that world-renowned mathematician Sir Michael Atiyah referred to it as beautiful, far-reaching, and totally unexpected. So, what is Bott periodicity? In order to explain the result, we first need to think about some of the most symmetrical objects we know of: circles and spheres. Here is something you might not know. Spheres come in different dimensions. For example, the common circle is technically a sphere in the second dimension. The common sphere, like a hollow basketball, lives in the third dimension. We can keep going. There is a sphere that lives in the fourth spatial dimension, the hypersphere. This is impossible to visualize, but just because we can't see it doesn't mean we shouldn't study it. So what makes the circle and the sphere so symmetrical? What is symmetry? A symmetry of an object is a transformation that leaves it looking the same. For example, if we rotate a square by 90 degrees, it still looks the same. This is one symmetry of the square. What about a circle? A circle is highly symmetrical. We can rotate the circle by any angle. We could also reflect two halves of the circle. So the circle has many symmetries. This is what makes it so beautiful. The technical name of the collection of all symmetries of the circle is O2. Now, let's go up a dimension and study the symmetries of the sphere. The sphere has even more symmetries. We can rotate it like the circle, but we get to pick an axis to rotate it about first, like a spinning top. We can also reflect the two halves of the sphere. Think of slicing a basketball in half. The technical name of the collection of all symmetries of the sphere is O3. We could study O2 or O3, and there are plenty of interesting things to say about them. But we could also study O4, the symmetries of the sphere in the fourth dimension, the hypersphere. For that matter, we could study the symmetries of the sphere in any dimension. But wait, look at the sphere again. There is a circle on the surface of the sphere, the equator. And some symmetries of the sphere are also symmetries of the equator, like this rotational symmetry. Actually, any symmetry of the circle can be seen as a symmetry of the sphere. In other words, O2 lives inside of O3. Or you could say, the symmetries of the circle live inside the symmetries of the sphere. This pattern continues. Just like the sphere has an equatorial circle, the hypersphere has an equatorial sphere. But as this is in the fourth dimension, and we exist in the third dimension, it's hard for us to imagine. So not only does O2 live inside of O3, but O3 lives inside of O4. O4 lives inside of O5, and so on. So instead of just studying O2 or O3, we can instead collect all of these symmetries into one big set called O infinity. If that's a bit daunting, then you can imagine On for some very big number n. Our beautiful fact about Bott periodicity is all about this big collection, O infinity. We have just one more piece of mathematical technology to learn about. Mathematicians use something called homotopy groups to help them understand shapes and spaces in every dimension. Homotopy comes from two Greek words, homos meaning same or similar, and topos meaning place. So homotopy is to do with two places or spaces being the same or similar. There are several homotopy groups, which we call the first homotopy group, the second homotopy group, etc. The first homotopy group measures loops in a space. The second homotopy group measures loops of loops. The third homotopy group measures loops of loops of loops, etc. So, what's a loop? Let's start with an example. Imagine you're in an enclosed courtyard and that there is an out-of-bounds water fountain in the center. One way to kind of map out the courtyard would be to study all of the possible walks we could take in the space. For example, let's start at a particular point and think of all the possible paths we could take that start and end at this point. We call walks or paths that start and end at the same point a loop. There can be lots of different homotopy types, or loops, within the first homotopy group of a space. The first homotopy group contains all the possible different types of loops possible in the space, in the sense of homotopy. Let's look at these 3 loops. There's something similar about 2 of them. We say that one loop is homotopic, or similar to, another loop if you can deform or merge one into the other. We're on our way to understanding the first homotopy group of the courtyard. So, returning to our study of the courtyard space, let's search for all the different loop types within the first homotopy group. Here is a homotopy, or deformation, of one loop into the other. In fact, both of the homotopic loops can be deformed or pulled tight to a very boring loop, the loop where you don't move at all, you just stay put, i.e. a point. But any loop that goes around the water fountain can't be pulled tight to a point, so it's fundamentally different to the others. So it's different in the sense of homotopy. There are many different loops that can be pulled tight. These are all the same type. Is that all the possible loops in the courtyard space? You might notice some others. For example, you could loop around the water fountain anti-clockwise. If it goes in a different direction around the water fountain, it's a different homotopy type. But what sets 2 loops apart, in the sense of homotopy, is the number of times a loop loops around the water fountain, clockwise plus or anti-clockwise minus. Let's call this number the winding number. So the first homotopy group contains an infinite number of possible loops, each associated to a unique winding number. As a reminder, if we remove the water fountain, the first homotopy group would only contain one loop type, since all the loops could be pulled tight to a point. What about the second homotopy group? So, if the first homotopy group measures how many loops are possible, the second homotopy group measures how many loops of loops are possible. Let's see an example in this space, a room with a sphere hovering in the middle. A loop of loops is a special loop where each point on the loop is another loop. Here is a loop of loops that start and end at a point. So, if the first homotopy group has something to do with pulling a one-dimensional rope tight, then the second homotopy group has something to do with pulling a two-dimensional net or sheet tight. Notice that this net cannot be pulled tight because of the sphere it encloses. What about the third homotopy group? This counts all the possible loops of loops. In order to maintain our sanity, let's call these 3D loops. And loops of loops we'll call 2D loops. You could think of a 3D loop as a loop of 2 loops. However, this gets difficult to visualize since we exist in the third dimension. The amazing thing is that even though we can't visualize 3D loops, 4D loops, and so on, we can still study them. This is the power of mathematics. It allows us to study things that are impossible for us to visualize. Let's now apply what we've learned to symmetries of spheres. Remember O3, the collection of symmetries of the ordinary sphere? What would a loop in O3 look like? Well, it would be a loop of symmetries of the sphere. At each point on the loop, we'll rotate the sphere about a vertical axis. However, we'll also rotate the vertical axis itself. Combining these 2 rotations leads to a loop of symmetries of the sphere, aka a loop in O3. Even more fascinating is that this loop is like the loop around the water fountain in the courtyard in the sense that it cannot be pulled tight to a point. In other words, there's a kind of hole in O3 which is detected by its first homotopy group. Don't worry if you can't visualize this. It's very tricky since O3 is actually three-dimensional. You might be thinking, how on earth could you be so sure that you can't pull this loop tight if you can't see it? The answer is with mathematics, of course, but that requires some level of understanding of algebraic topology. So, what was the result of Bott periodicity that Atiyah was so blown away by? Bott was interested in computing the homotopy groups of O infinity. Remember, O infinity is the collection of all symmetries of all spheres in every dimension. In other words, he wanted to know how many loops, 2D loops, 3D loops, and so on are possible in O infinity. This is what Bott found. In O infinity, there are 2 possible loops, only a single 2-dimensional loop, aka a loop of loops, an infinite number of 3D loops, each associated to a positive or negative whole number, and so on. Interestingly, the table starts repeating after 8 dimensions. If you look at the table, you can see that there are 2 1D loops, as well as 2 9D loops. That can happen sometimes, but hang on, there is 1 2D loop, as well as 1 10D loop. And there are an infinite number of 3D loops, as well as 11D loops. And the same number of 4D loops as there are 12D loops. Bott found an incredible pattern within these symmetries of spheres. He found an 8-fold periodic phenomenon that continues indefinitely. To put it differently, 1D loops in O infinity are equivalent to 1 plus 8 9D loops in O infinity, which are also equivalent to 9 plus 8 17D loops in O infinity, and 17 plus 8 25D loops, and so on. So the loop in O3 we looked at earlier is equivalent to a 9-dimensional loop of symmetries of spheres and a 17-dimensional loop of symmetries. Even stranger, a point in O infinity, which is a symmetry of a sphere in some dimension, is the same thing homotopically as an 8-dimensional loop of symmetries. Once again, a symmetry of a sphere is the same as a loop of loops 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 of symmetries of spheres. Take a moment to think about how insanely strange that is. So we've learned about symmetries of circles, spheres, and higher dimensional spheres. We found that the symmetries of the circle live within the symmetries of the sphere. We decided to look at O infinity, symmetries of spheres in every dimension. Then we talked about the 8-fold periodicity that Bott found in the homotopy groups. This repeating pattern in the number of loops, 2D loops, 3D loops, and so on. I don't know about you, but for me, this just raises more questions than it answers. Like, why 8? Why not 5 or 42? And what is it about symmetries of spheres that leads to this periodic phenomenon? To answer those questions and discover even more amazing patterns, you'd have to learn a great deal of mathematics. But I assure you, it's worth it.